Today, I start the new chapter of fluid mechanics, that is buoyancy and flotation. Let's try to understand this concept. So this is my handwritten notes. You can download it from the description. Don't write the notes. You can directly download the PDF from the description. Let's try to understand this. Body is submerged partially or completely in a fluid exerted upward hydrostatic force. Body is balanced in horizontal forces. This net upward hydrostatic force is known as buoyant force. The buoyant force is the weight of the fluid displaced in magnitude, and its point of application is the centroid of displaced fluid known as center of buoyancy. Let's try to understand this. So consider this is a fluid surface. There's any fluid are there. It may be water, it may be air, it may be any fluid. Okay, now consider this is a liquid water is there. Okay, and this is the free surface. Now here our body, this is our body, and this body is kept here. So when this body come in the fluid, inside the fluid, then there is a pressure force which is compressive in nature. So due to this pressure force, if we divide the horizontal force and vertical force, then we will get, so this is the same surface here, this is the same body. Now there is a vertical component, there is a horizontal component are there. So this is one area. Now this is the horizontal component, so this is in right side, and there is a horizontal component from the left side. Now so horizontal force, if you want to calculate the horizontal force, that is Fh1, and horizontal force from right side, that is F2. G is the center of gravity. Now AP is the projected area. So what is AP? That is the project. Consider this is the projected area. Now if you want to calculate the horizontal pressure force, that is omega AP into x bar, we know that omega, that is the specific weight, that is rho into G into area of the plate, projected area, into x bar. What is x bar? So from the free surface to this centroid is known as x bar. So if you multiply these three properties, then you get Fh1. Okay. Now similarly, if you want to calculate the Fh2, that is equal to omega AP into x bar. So you see that here also omega AP x bar, and Fh2, that is equal to omega AP x bar. So they are equal and opposite in nature. So that's why they are cancelled to each other. So that is why there is no horizontal component are there. Now there is another component, that is vertical component, and this is our body. Now the vertical component which is acting on the body, so this in this side, consider this is Fv1, and the vertical component of the body just downside here, this is Fv2. Now if you want to calculate the net force, that is Fv2 minus Fv1. What is Fv2? This is in this side force. Okay, and Fv1 here, the force is Fv1. Now if you want to calculate net force, that is F net, that is Fv2 minus Fv1. Now the case is that here Fv2 is greater than Fv1, that's why Fv2 minus Fv1, and this is known as buoyancy force. Fb means buoyancy force. Now what is written here? So Fh1 and Fh2 is balanced, so resultant force is upward direction. So if you want to calculate the resultant force or buoyancy force, that is F net, that is equal to Fb, that is equal to Fv2 minus Fv1. So this is the concept here. So this is written here. Okay. So this is my handwritten notes. You can download it from the description available. Don't write the notes at this time. Just understand the concept. Okay. Now here consider this is a body, and this body is inside any fluid. Now the buoyancy force which is acting upward direction here. So in balanced condition, this body have the buoyancy force that is in upward direction, and here this point is G, center of gravity. Now there is a formula. If you want to calculate the buoyancy force, how to calculate this buoyancy force? That is equal to weight of the fluid. Now how you want to calculate the weight of the fluid? Now the concept is that suppose there is a pot here, and this is full of water. Consider that this body is not there, so there is a pot, and this is full of water. Now if you kept one body here, so if you want to kept in body in this portion here, the fluid which is displaced from this pot, and this is coming down to this lower pot. So from here you can get the weight of the fluid displaced from the pot. So if you measure the weight, you can get the weight of the fluid displaced from the pot. So if you want to calculate the buoyancy force, that is equal to weight of the fluid displaced. That is the main fundamental concept. You have to remember, this is very important concept. Now there is one principle that is also important, that is Archimedes principle, or it is also known as principle of flotation. What is this? When a body is submerged in a fluid partially or completely, then in equilibrium condition the weight of the body is equal to the weight of the fluid displaced, and the body is said to be floating. Very important. Okay, so suppose this is any liquid are there here, and this is the free surface symbol. Now there is a body. Now this, keep this body, when the body is placed here, the body, suppose this is the body location. Now if you want to calculate the weight of the body, so how to calculate this weight? That is the omega b into v. Omega b, that is rho into g into omega, that is specific weight, that is rho into g into, and v is the volume of the body. So if you want to calculate this volume, and if you know the density of the body and specific gravity, then you can directly calculate the weight of the body. And now if you want to calculate the buoyancy force of the same body, how to calculate that? If you want to calculate the buoyancy force, the formula is Fb, that is equal to W of fluid Fd. So what is WFD? That is weight of the fluid displaced. Very important. So how you want to calculate the weight of the fluid which is displaced? That is equal to density of fluid, not the density of body here. If you want to calculate the buoyancy force, you have to multiply density of fluid. You have to take the density of fluid into G into volume of the fluid displaced. You have to take the volume of fluid which is displaced. So this is how we calculate the buoyancy force. Now at equilibrium condition, so weight of the body, that is equal to buoyancy force, and this is known as floating condition. Now suppose density of body is greater than density of fluid. So in any case here, if the density of body which is submerged on a fluid, if the density of body is greater than density of fluid, then density of body into G greater than density of fluid into G. Just multiply it on both sides. Now density of body into G into V, that is greater than density of body, density of fluid into G into V. So from here, weight of the body, that is greater than buoyancy force. Okay, so if the weight of the body is greater than buoyancy force, the body will come down in the fluid. Okay, now the concept is that, suppose there is a ship is there, and this is seawater is there here, and this is the seawater free surface. Now, and there is a ship, and the depth of the ship, the height of the ship from the free surface, consider this is h. So here the buoyancy force which act in the upward direction, and weight of the body, this is the G point, so weight of the body which is downside direction. Now if you want to calculate the buoyancy force here, that is the rho of fluid G into VFD. Okay, now if you want to calculate the pressure force, so if you want to calculate the pressure force, P into area, so we know that what is P, that is equal to rho G H and area. So here rho G H into area. So this is the pressure force here. Now if the same ship is in the river, what happened? So this is the sea water and this is the river. So if the same ship in the river, what happened? So this is the river free surface here, and this is the center of gravity. So buoyancy force is acting in upward direction, and this is the ship which is downward direction, and here the height, that is capital H. So remember here, this height is greater compared to this height. Why? Because if you want to calculate the buoyancy force here, that is the rho of fluid G into volume of the fluid displaced. Now here what is happened, as the fluid density, so here the density of water is less than density of sea water is greater than density of river. So in that case, density of the fluid in the river is less as compared to this. So volume of the fluid displaced should be larger. Height from here to here is greater than this height, because here the density is large as compared to this. So that's why the height H is greater than this height.